Hello, hello. Let's see. Oh, I just got your message, Camilla. Um, let's see. Just wants to ask if Acidity and E2 isn't it NH2 and EDG? Yes, NH2 is an EDG.
I think I drew that one wrong. Like I feel like the double bonds would be different,
Yes,
right?
NH2 is an EDG. Um, so the EDG would be on the sp2. So let me share my screen.
Thank you.
Yeah, uh-huh. Mhm. Let's see. Yeah, start right here. Okay. So this is the benzene with the groups that it's attached to, reacting with these reagents, Na, NH3 liquid, and ethanol, the Birch reduction reagents, where the product we have two alkenes that are unconjugated, cannot do resonance. And to predict the product, we want the EDGs on the sp2 carbon, and we want the EWG on the sp3 carbon. So this would be the correct answer because all the EDGs on an sp2 carbon, and the only EWG is on the sp3 carbon, like that, right? Because if we think about the intermediate here, the negative charge is on the sp, like what used to be the sp3 carbon, and that negative charge is more stabilized by the EWG here because it can do resonance with the EWG and it wants to stay far away as possible from the EDGs because like charges repel each other, opposite charges attract.
Okay, I see. Thank you.
Yeah. Chapter 22 practice problems tonight. Yeah. We could go over chapter 22 practice problems tonight. Did you want any like random chapter 22 topics problems?
Yeah, like full
Uh-huh.
chapter,
The whole
anything.
chapter? Oh shoot. Okay. Let me see. Let me try to make some up, and then while I make them up, you could try them out, and then
Okay.
I'll move on to what is in A or Johanna Ocam one.
Okay. Thank you
Uh-huh.
so much.
Yeah, no problem. Let's see. Okay. Okay, let's do this one. Import, open this one here. Okay. Let's do. Okay. Okay. Oh yeah. While I make this, Wiley and Johanna, what do you guys want to go over? You could tell me in the chat or uh tell me in through the voice. Let's see. Okay. Okay, Camila, try these six right now, and then we'll go over them, and then I can give you the rest of chapter 22 after you try these six.
No worries. Thank you so
Uh-huh.
much.
Yeah, uh-huh. Okay. So, yeah, so Wiley asked for equivalents in terms of alkyne reactions. Um, and then Johanna asked for substitution elimination reactions. And hey, Elysia, which when I go over those substitution elimination reactions, I'll go over that with Elysia because she has her midterm on that tomorrow, like the substitution elimination reaction. So uh, hopefully when we go over those, that would make sense for you too, Johanna. Okay, so did you have a screenshot of this yet, Camila?
Oh, yes. Thank you.
Yep. Okay, so equivalent in alkyne reactions. Yes. Terminal and internal alkyne deprotonating. Yes. Okay. So let's talk about formation of an internal alkyne versus a terminal alkyne. So let's first talk about an internal alkyne. Right. Before we talk about the reactions, let's talk about what an internal alkyne is versus a terminal alkyne. An internal alkyne is when the alkyne is on the inside of the molecule. For example, something like this, right? Where we see that this is an alkyne, C triple bond C, inside the chain, the molecule here. Whereas a terminal alkyne is at the terminal end of the chain or the molecule. So for example, something like you could say this, right? Where this alkyne here, C triple bond C, is at the end of the molecule, where all terminal alkynes will have a sp carbon hydrogen bond, right? Where this carbon is sp hybridized, making this the sp carbon hydrogen bond, right? So now to make an internal alkyne, what we could do is, like let's say we make it from an alkene. Like let's say this alkene right here, and we want to make this alkyne like this, right? Where this is 1, 2, 3, 4 carbons. That's going to be this 1, 2, 3, 4 carbons right there. To do that, we have to think about what reaction makes double bonds or triple or like a pi bonds. Yeah, let's say that. What reaction makes pi bonds, which is going to be the elimination reactions, right? Like E1, E2 type reactions. So if we want to do an E1, E2 type reaction, we have to have good leaving groups and a very strong base. Oh, you didn't learn E2 yet? What the heck? Okay. That's at end of the quarter. Okay, let me just teach you E2 right now, because this is part of the formation of internal alkyne. You need to know E2. You need to know E2 for this reaction. Okay, so okay. Have you learned about good leaving group? Yeah. Send a screenshot of your notes so that I can see what you're learning, so I don't like teach something different. Yeah. That would be helpful. Let's see. Okay. Let's see here. Okay. Yes. Base. SN2. Okay, I see. Yeah. So that right there is talking about making a terminal alkyne into an alkynyl anion. So that's totally different than this. So let's not go over this to not overwhelm you. Right. Okay. So we know this is a terminal alkyne. Before we go over those reactions, let's talk about this terminal alkyne sp hydrogen right there. Right. This, let's say if we compare it to this hydrogen and let's say this hydrogen here, do you know which hydrogen would be more acidic and why? It's okay if you don't. I'm just seeing like where we're at right now, so then I could go from there. Yep, the alkyne hydrogen. This alkyne hydrogen would be the most acidic because it has more s orbital character, sp. Yes, that's correct. This carbon here is sp. This carbon here, sp2. This carbon here, sp3. Right? What sp has 50% s character, sp2 has 33% s character. sp2 has 33% s character. sp3 has 25% s character. And the more s character an atom has, the closer they are to the nucleus, right? Which is positively charged. So when we draw out the conjugate bases, like let's say some kind of base is around and deprotonates those hydrogens, we are going to get these conjugate bases here, right? Where this negative charge here is the most stable negative charge because it is the closest to the nucleus, positive charge, and opposite charges attract, right? So they want to be close to the nucleus. And because they are very close to the nucleus, that makes them very stable. And if they are very stable, they are less reactive, making them a weak conjugate base. And weak conjugate bases come from stronger acids, right? Where the pKa of a terminal alkyne hydrogen is around 25. pKa of an sp3 carbon is around 50. And then I can't remember the sp2 is like 41 or something, but let me double check that. Let's see. pKa of sp2ch. 44, 45, 44, let's say. 44. Right. Where we see that the lower the pKa, the more acidic the molecule is. So this has the lowest pKa because it's the most acidic hydrogen. Right. So the base that we tend to use to deprotonate that terminal alkyne hydrogen is NH2 minus, right? Where whenever we see a sodium ion or a potassium ion, we associate that with a positive charge. And whatever is attached to that positive charge is negatively charged. So a negative charge here is this NH2 minus, which acts as our strong base in this reaction, strong base. And we said earlier that this is going to be our most acidic H in this molecule, right? Acidic H. So what's going to happen is that this NH2 is going to grab that H, and then the bond between that H being grabbed and this carbon is going to break and go onto that carbon right there, right? The two electrons in this bond are going to break and go onto that carbon right there, giving this conjugate base here, like that, right? Where we call this an alkynyl anion. Alkynyl anion. Anion because it is negatively charged. Right. And you can say like we formed NH3 as well from this NH2 grabbing the H, but this is not organic. So you don't have to put that in the predicted product or mechanism. Or actually mechanism, you have to draw that side product out. But this is the important thing we're worried about here. The negative charge on that carbon. Right. Where this negative charge on that carbon right there is going to be our base or nucleophile. It could do a lot of reactions. Right. That's going to be our precursor. So let me give you that again right here. NH2 minus. I'm going to draw in this form because you can see it as in the form of NaNH2 or KNH2 to give us this base or nucleophile. And this base or nucleophile, what I've learned is that it could do 5 different reactions. Let me just write these reactions out right now. Okay. And then this is going to segue into our next topic we'll talk about, which is going to be substitution and elimination. Okay. Wait, no, this is a separate reaction. Okay, so this is going to be reaction 1, reaction 2, reaction 3, reaction 4, and then reaction 5. Okay. So I'm going to also draw out the mechanism for each reaction to make it more sense for you. Let's say for reaction 1, we are reacting this alkynyl anion with this H3O+. What that's going to do is an acid-base reaction, right? Where this alkynyl anion will act as a base grab one of the acidic H's of the H3O plus acid, hydronium ion, and then kick out a water molecule to give us this neutral terminal alkyne back and water, like that. So that was just an acid-base reaction where the alkynyl anion was the base and the H2O plus was the acid. You could have used H2SO4 as well, sulfuric acid, to protonate this base. Yeah, there are names to the reactions, but like it's not very clearly defined because you could describe it in many ways. You could say this is an acid-base reaction or protonation deprotonation reaction. This one for sure there's a name. Like this is gonna be SN2, this is gonna be E2, but you haven't learned about that yet. But let me check your notes if she put that there. Yes, she did. She did put a primary haloalkane there, which is SN2. So there is an SN2 reaction here as well. I know. Yes. That's weird. Like you should learn SN2 first before learning this stuff. Okay. Because you have to know the definition of what a nucleophile is, what an electrophile is, and what a leaving group is. Have you been taught those terms before? Nucleophile, electrophile, leaving group, substrate. Nucleophile, electrophile, yes. Okay. What about leaving group? Okay. Not really. Okay. But did the first reaction make sense for you here? The acid-base reaction? Like, okay, that's a Gen Chem thing, the acid-base reaction. This is gonna be the new material, SN2, E2, and then this is gonna be new as well. So before we go over those, I'm gonna go over substitution and elimination with Johanna and Elysia. And then after that, we'll go back and this will make more sense. Okay. So hey Elysia, hey Johanna, do you want to go over the homework last night I gave you, Elysia?
Oh, sorry. Yeah, yes, please.
Yeah, let's go.
I sent it through Discord as my work.
Yeah, thank you. Let's see, let me go find that right here. Let's see. This one. So it's gonna be these 5 problems. See. What time's your exam tomorrow, Elysia?
It's at 8.
8. I see. 8 a.m.
Yeah.
That's first thing in the morning. Okay, let's check your work. Let's see here. This one. Oh, I got it. Let's see here. Save. Okay. Share screen. Okay. Ooh, let's see. What's going on here? Let's see. Yep, inversion. SN2. Okay. This one, weak. Yes, this is a weak nucleophile. But be careful here. This oxygen does not have a full negative charge. It does have a partial negative charge though. Partial negative charge with 2 pairs of electrons. Right. So we don't want to draw the negative charge in this format because it looks like it has a full formal charge of -1. Right. It's neutral, making it a weak nucleophile. Good leaving group, secondary. SN1. Yeah, nice. Where the first step of the mechanism is to kick out the leaving group, form the carbocation. Stop at the carbocation. And yeah, so before we do the SN1 product here and attach the nucleophile to the electrophile, that's good that you put both the wedge and dash product because this sp2 carbon right here is flat and planar with the positive charge. So when the nucleophile comes in to attack the carbocation, it could have attacked on the top side, giving us the wedge product, or the back side, giving us the dash product, right? That's correct. But before we do that, we have to see if we can do any rearrangement steps, right? We have to see if we can do any hydride or methyl shifts to make the carbocation more stable, right? So to do that, look at the carbocation right now, and then look to the left and right of it, which is going to be this carbon and that carbon. Is there any position that you see that can become more stable? The carbocation can become more stable?
Yeah, the one on the left.
Yep, the one on the left. So what we could do is draw out that hydrogen out explicitly and do a hydride shift. Move that bond with the hydrogen to that carbon right there to get this intermediate here, right? Where that carbon lost the bond, giving that carbon a positive charge, right? And then the hydrogen that we moved is on this carbon now, making this carbon neutral, right? Because it gained the bond. So we shifted the carbocation from a secondary position to a tertiary position. So now this is the more stable tertiary carbocation, where when we predict the product for SN2, the nucleophile here is going to attack that carbocation and make this new bond between the oxygen and carbon, which this oxygen here that attacked that carbon is this oxygen right here, which is attached to a hydrogen, which is this hydrogen here, and an ethyl group, which is this ethyl group here. And because it has 3 bonds, it's positively charged. The last step of this mechanism is to get rid of that positive charge, make it neutral. Right, by using another alcohol as a base to come in and deprotonate it, like grabbing the hydrogen of that oxygen, and the 2 electrons from this bond here is going to break and go onto the oxygen right there, giving it an extra pair of electrons and making it neutral. Final answer here, the OCH2CH3, like that, which is this OCH2CH3. And this would be a wedge or dash, but I don't draw that in the final product here because this is not a chiral center. If it was a chiral center, then we would have to put wedge and dash product, right? Like let's say this was a methyl group, then the methyl group would have been a dash and this would have been a wedge and vice versa. But because this is not chiral center, because we have 2 ethyl groups on that same carbon, we don't have to put any wedges or dashes.
Could you explain like the second to last step that you did, where like there's the OH and the OH electron pair is going to the hydrogen?
Yeah. So the second to last step. Oh, this step right here.
I guess you could do like that one and the one after it.
Okay. Yeah. So for this one right here, once we have our carbocation, this carbocation here is going to be considered our electrophile, right? Because it has the full positive charge. So it loves electrons. Electrophile for electron, electro, loving phile. And they are electron loving because they are positively charged. That loves electrons which are negatively charged. Opposite charges attract. This oxygen right here with the partial negative charge and 2 pairs of electrons is going to be our nucleophile, right? Because nucleophiles are negatively charged and they love positive charges. They love the nucleus loving. And in OChem, nucleophile will always attack electrophiles. So this oxygen right here is going to use one of its pairs of electrons to attack this carbon here with a positive charge, right? And you could say that this nucleophile is attacking this electrophile. And in OChem, the reactions will always go from a nucleophile to an electrophile. So we're making a new bond between the oxygen atom here and this carbon atom here, which is this new bond here in the next step. That new bond comes from this pair of electrons right there, right? Because every bond has 2 electrons, 1, 2. Those 2 electrons are coming from that pair of electrons right there, right? Which is why we see in the next step, this oxygen right here has only 1 pair of electrons left because it used its other pair of electrons to make this new bond between the nucleophile and electrophile, between itself, between the oxygen and that carbon right there. That's the new bond that we formed. And this oxygen right here is also attached to an ethyl group, which is this ethyl group right here, ethyl group right there. It's also attached to a hydrogen, which is this hydrogen right here. So that's this step right here. Nucleophile attack electrophile to give us this intermediate right here, to make a new bond between the nucleophile and electrophile.
You said that's the intermediate?
Yeah, and this is the intermediate. Yeah, right. Does this make sense so far on why, how we got this with the positive charge on this oxygen here?
Okay, so I think so. So just to clarify,
Yeah.
we from the step like previously before, we wanted it to be into like a more preferable position, which is our tertiary positions. We moved it to the one with the tertiary carbon, and then after that we have our is it our nucleophile that's able to attack the positive because it's able to, it's ready for it to like attack it. And
Yep. Right. It prefers to attack the more stable carbocation over the less stable carbocation.
right. I think I'm just a little bit like confused on how you drew the part after, like how you drew it, because it looks kind of.
Oh, this one right here?
Yeah.
Yeah. So let me draw that out in this form right here. So this is the nucleophile with its 2 pairs of electrons. This is the electrophile carbon. Right? Where does that arrow make sense on why that oxygen is attacking this carbon right here? This is the carbon it's attacking right here, right? I'm gonna dot that carbon representing the electrophile. I'm gonna star this oxygen representing the nucleophile. Whenever a nucleophile attacks an electrophile, or what I like to call the star dot technique, the star is the nucleophile, the dot is the electrophile. So I'm gonna draw out the molecule with the dot like this. So this is gonna be the dot carbon right here, which is also attached to an ethyl group, but I'm gonna draw that ethyl group, let's say go face towards this way, right? Different angle. But now I'm gonna make a new bond between that dot carbon and this star oxygen right here, right? Because our nucleophile is this oxygen right here. And this is the new bond between the star and dot atom. New bond. And that new bond came from that attack. Does that make sense so far?
Yes, it does.
And now, what is attached to this star oxygen here?
Hydrogen?
Yep, 1 hydrogen, that's right. And I'm gonna draw that 1 hydrogen out like this. What else is attached to this oxygen here?
Lone pairs?
How many? Ethyl group, which is this ethyl group here. Yep. So I'm gonna draw the ethyl group right here. And before there used to be 2 lone pairs of electrons, but now there's gonna be only 1 lone pair of electrons, which is this one right here that did not react. This one here is gone because that one made this bond right here. That one lone pair made that new bond between the star and dot when it attacked the dot.
Okay, that makes sense.
Mm-hmm. Yeah, and what would be the formal charge of this oxygen here? What's the formal charge of this oxygen?
A plus.
Plus charge, right? Plus charge, right? So to get rid of the plus charge, we want to neutralize it, making it neutral. So we have to deprotonate it. And we deprotonate it by using another alcohol as a base to grab that hydrogen, and then give that oxygen a pair of electrons from that bond between the hydrogen being grabbed and the oxygen right there, which gives us this neutral product here. Right.
Oh, okay, I see it.
Yeah. So that would be the mechanism if they ask for the mechanism on the test, like the mechanism meaning the arrows representing how we get to the final product from the reactant, right? Like all these arrows and intermediates are part of the mechanism.
Okay, so
Okay.
we just assume that there's another like OH there floating around, like we had another one come in.
Yes, we have excess amount of ROH, alcohol. Right. This is gonna be the second equivalent of the ROH, where the first equivalent of ROH was used to attack the electrophile, like that. And then another ROH, the second equivalent, just comes around to deprotonate. Right.
Okay.
Okay. So that's SN1. There's also E1 product, but that's minor. Where the E1 would have the same first steps. Leaving group leaves first, form the carbocation, stop at this carbocation intermediate, do the shifts that you want if you can to get the more stable carbocation, and then this is where it's different. Right? Once you have the most stable carbocation intermediate, you then find your let's say this is your alpha carbon. These would be your beta carbons. Draw out at least one beta hydrogen for each beta carbon. And then see which one is the most substituted beta hydrogen. They're both all like equally substituted. So you could have grabbed any one of these hydrogens with the base, like let's say another equivalent of the alcohol, to come in, grab that hydrogen, and then the bond between that hydrogen being grabbed and that carbon is going to make a double bond right there between the carbon and the carbocation to form this alkene here, double bond, like that. That was E1, right? And this is going to be our major E1 product, which is going to be the same if we grab this hydrogen or that hydrogen. It's going to be symmetrical, right? If we grabbed this hydrogen, we would have gotten this product. If we grabbed this hydrogen, we would have gotten this product here, right? Because when we grab the hydrogen, it's going to make a double bond right there towards the positive charge. And all of these molecules here are the same. They are identical, right? It's just rotated. But in other cases, you would have to choose which hydrogen to choose. For example, let's say we have this carbocation right here. And this is your alpha carbon. These are your beta carbons. Which beta hydrogen would you grab, A or B, to make the more stable alkene, the more substituted alkene?
I would do the B.
Yep, B, right. So some kind of base, usually the alcohol or water for E1, is going to grab that hydrogen B, make a double bond there, and that's it for E1. Boom, like that. Oh, another thing is that this single bond can do free rotation. So because it could do free rotation, the intermediate could have rotated like this, where when we grab that hydrogen B, we could have gotten this alkene as well. But which one do you think is major here? This alkene or that alkene?
The top one,
Yep.
because they're trans.
Yep, major, minor, trans, cis. And that's because the cis has more steric hindrance. Those two R groups are bumping into each other, causing steric hindrance, which makes it less stable. And that's why it's minor. That's why cis is minor compared to trans, because they have more steric hindrance. Yeah. So that's E1, which is minor than the SN1 products. Okay. Yep. So for the next one right here, we do have a strong base, which is small, and we do have a good leaving group. CH3, 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 tertiary. That's good because this carbon is attached to 3 other carbons. And you could have grabbed the hydrogen from here, here, or here. Right? And since this is a small base, we want to grab the hydrogen from the most bulky carbon, which is this one. That's good. You grab the correct hydrogen. Which when we grab that hydrogen, there's going to be an arrow from that bond going to that carbon right there, making that double bond right there. Kicking out the leaving group, chlorine, that's good. Which is going to give us, yep, nice first arrow, nice second arrow, nice third arrow. So those are the correct mechanism arrows. And then if you were to draw out the whole product, this is the product that you would get. So the mechanism arrows are correct. Here is what the product would look like after everything here. Like that. And Cl minus that left. And you say CH3OH. Yeah. Okay. Which gives us this tetra substituted alkene.
Oh, okay. So instead of like drawing the double bond like where I put it, we have to draw out again where as the final product.
Oh, did you put the double bond here as the product?
Yeah, but I probably shouldn't have.
Yeah. The double bond is not there yet. Yeah. That double bond is not there. The arrows are happening first. This arrow here is creating that double bond. It's not there yet. Yeah, so don't draw that double bond there. Right. But in your mind, you would think that there's gonna be a double bond right there. Right. Yeah. So the mechanism would look like this right here. Cl, boom, boom. Draw that H. OCH3 minus. Grabs that H, make a double bond here, kick out the leaving group, give us our final answer like that.
Okay, that makes sense. Thank you.
Yep. Okay, next one. Yes. So good leaving group. This one here is going to be a bulky base now, hindered base, because this is butoxide. So this is not SN1 reaction. So the leaving group will not leave first.
Yeah, it'll end up being would it be? Oh, it's gonna want to do Hoffman, right?
Hoffman, yep, Hoffman, right. So for Hoffman, what is going to happen in Hoffman here? Hoffman E2.
It's going to want to go to a spot that is more available or less crowded. So like,
Yep.
I'd say like either that one, yeah, or the other side. Either or, I think.
This one, or this one. Right. This is a sneaky one because a lot of people forget about this thing here, the methyl group. Right, because this is the alpha carbon. These are the beta carbons. The least substituted, the most available beta carbon is this one right here on top. That one right there. Right. So the tributoxide is going to come in grab that hydrogen, make a double bond, kick out the leaving group, give us this final answer here. For the Hoffman E2 product.
Do we have to draw it out?
The mechanism?
Like the nucleophile?
To draw the mechanism, yes, you do. You could have done it like that, or you could have done it like this. Like that, in condensed formula. But I prefer to say it in line form. Right. But if you use a small base like NaOH, OH minus, that's gonna go for the Zaitsev E2, grab the moist substituted H, make a double bond, kick out the leaving group, and give us this alkene here. Like that. And this is the Zaitsev product using a small base. This is the Hoffman product using a bulky base. All right. And even if you kick out this leaving group right here, you're removing that bond. So that bond will no longer be there. Right. So after we kick out that leaving group, if we do, this would be the intermediate right here. Right. Where this pink carbon here is the carbon that lost the bond, giving that carbon a positive charge. Like that. Right. That bond is no longer there because it left with the leaving group. Whenever a leaving group leaves, it leaves with the bond that it was with.
Okay, that makes sense. And if you said if we were to do Zeitzen?
Yep.
How would that work again?
Yeah, so Zaitsev would be using a small base. So we would want to get the most substituted H. So it could have been this hydrogen or this hydrogen, the most substituted H. Right. So when the small base grabs that most substituted beta H, that would form, like in this case, water. If we use OH minus, the bond between the H being grabbed and that beta carbon is gonna break to make a double bond here between the alpha carbon and beta carbon, and then kick out the leaving group at the same time. So in E2 reactions, 3 arrows happen at the same time. The first arrow is to grab the H. The second arrow is to make the double bond. The third arrow is to kick out the leaving group. All those 3 arrows happen at the same time for E2 reactions, right? If we look at the Hoffman using the bulky base, that's going to grab the hydrogen that is the least substituted, which is this hydrogen here, make a double bond here between the alpha and beta carbon, and then kick out the leaving group. All those 3 arrows happen at the same time.
Okay, so Hoffman can still be like a same step thing. It's like either Hoffman or Zaitsev.
Oh, the same arrows, yeah, same mechanism. Hoffman is the same mechanism arrows as Zaitsev, yeah. But they're different in that they choose a different hydrogen. Hoffman chooses the less substituted hydrogen. Zaitsev uses the more substituted hydrogen. The reason why is because in Hoffman, we use the bulky base. The bulky base can only go for the most free hydrogen, can go for the least sterically hindered hydrogen, but that leads to the less stable alkene, the less substituted alkene, right? But if you use a small base, it can grab the more substituted H, making the more stable alkene. Yeah.
Okay, and also to know for the one below, I'm pretty sure it's Sovalysis, but I didn't think that at first, and I realized after like I sent it that I may have done that wrong for sure because H2Os
Uh-huh.
it can react
Uh-huh.
but it would do Sovalysis.
Yeah, it
So
would do SN1 here with the secondary carbocation, weak nucleophile. If you look at the table chart, SN1 E1, right? So Sovalysis to make the leaving group leave first, which would give us this carbocation. And then what do we have to do once we have the carbocation here? What do we have to watch out for? before we attack the carbocation.
Okay.
Yeah. So after this step, what would be the next step?
Well, I think that the positive will want to go to a more substituted spot.
Yep. And to do that, we have to do a hydride shift where this position has a hydrogen that we can shift to that carbocation to make it into the more substituted spot, like that. And then water comes in to attack to give us this intermediate. New bond between the nucleophile electrophile. Oxygen is still attached to its two hydrogens, but because it has 3 bonds, 1, 2, 3, it has a positive charge. So to neutralize that positive charge, we can deprotonate and neutralize it with another water molecule to give us our final answer here. And because this is not a chiral center, we don't have to put wedge or dashes, right? But we would if this was a chiral center. Yeah, SN1.
So you're
Okay.
saying like we draw a hydrogen and then we draw it to that one spot that we used to have it in, and then giving us like a more substituted or like a more preferable spot to have a carbocation.
Yep. And that's what we call a hydride shift. We're shifting the hydrogen to the carbocation, which is going to be this hydrogen now, making this carbon neutral because it gained the bond, but this carbon here lost the bond. Right? This carbon here lost the bond, making that carbon positively charged, but that's the driving force because this secondary carbocation here became a tertiary carbocation. It has more friends, making it more stable. And that's why we do that hydride shift. And then once we have the more stable carbocation, we do the rest of the mechanism. Yeah.
And then we just expect there to be another water molecule to grab the hydrogen, and we would have a side product of H3O plus.
Yep. Side product of H2O plus. That's
and
right.
we would then end up getting like a stable OH instead of unstable from how it was before.
Yep. Right. Yeah. Yes, this is neutral. This is positive charge. We want to get rid of that positive charge, so we take in another equivalent of the H2O or ROH, whatever we have in the reactant. Before it was ROH, now it's H2O to deprotonate and neutralize to get this stable neutral product.
Okay, that was a good one. Thank
Yeah.
you.
Yeah, no problem.
So there was I think I had a quick question. So there was like I think one of the same guy that I brought up last time.
Oh,
He was
Anake?
explaining. Yeah, there was this. I think there was this thing where it's like NaO, CH2, CH2, CH2,
Yep.
CCH3, and that's
Yep.
considered a a strong base.
Yes, it is.
Like,
It is.
okay. Could you explain that? Because like he said that it's just a chain, but like I feel like I guess it's like it's a really long chain, so that would make it okay. Whereas like if it's like a CH3 CH2 O something, then that is like not a strong base.
Like this CH2, CH3 instead.
Yeah, something like that. That would be considered like a not a strong base.
That is also a strong base. Right.
Oh, okay. I think
So
it was like something like it wasn't like an NA, it was like something with an O at the end, and that was considered like
like not strong base.
yeah, something
Yeah.
like
So
that.
that's gonna be talk about this CH2, CH2, OH.
Yeah.
Yeah. So strong bases will have, in terms of SN2, SN1, E2, a negative charge on an oxygen or a nitrogen. Right. whenever you see Na, what charge does that associate with? Positive or negative?
Positive.
Yep, positive, right? And that means that whatever is attached to it is negative charge. So the O is attached to the Na, making that a negative charge O. And because this O is negatively charged, we consider that a strong base. Right. You could have also seen, let's say, something like this: CH3, CH2, O, K. Whenever you see potassium K, what charge do you associate that with?
Positive.
Yep, positive, making the oxygen what charge?
Negative.
Yep. And would that be a strong or weak base?
Strong.
Yep, strong base. Whereas if you look at this molecule here, this is not an A or K. That's a hydrogen. That hydrogen is directly bonded to the oxygen by covalent bond. So there's no full negative charge on that oxygen, making this a weak base. Right. Because there's no full negative charge on that oxygen, it's neutral. And because it's neutral, it's more stable. And because it's more stable, it's less reactive. And making it a weaker nucleophile, weaker base, or nucleophile, weak base, like that.
Okay, that makes sense. Thank you.
Yep. Mm-hmm. Okay. Okay. Let's see. Hey, Johanna. Let's see. You just started new material for your class. Did you start SN2, SN1, E1, E2 introduction yet? Yeah. Okay. So let's see here. Let's go back to the alkyne reactions, where when we see a negative charge on this carbon right here, this could act as a base or a nucleophile. Right. Where in the first reaction, we see that it's an acid-base reaction because we brought in an acid, where this will act as a base, protonating the alkyne. But now in the second reaction, let's say that we bring in this primary haloalkane right here. Right. This carbon here directly attached to the bromine, the electronegative bromine, its partial charge is going to be partial positive charge. Right. And because it's partial positive charge, we are going to consider that the electrophile. Right. Because electrophiles are positively charged, nucleophiles are negatively charged. This right here is going to act as our nucleophile. Right. So now, this Br here, think of that as a good leaving group. Right. And a good leaving group, think of it as a group that is able to leave with a negative charge or with an extra pair of electrons, can stabilize an extra pair of electrons, because when it leaves, it's going to leave with an extra pair of electrons. And that extra pair of electrons is coming from the bond. It's attached to. So this leaving group, when it leaves, it's going to leave with this bond right here that it's attached to. Right here. Yeah, that one. Right. Where now this is a primary electrophile substrate because this carbon here is attached to one other carbon. Right there. One other carbon. Right. And because it's primary, it has a lot of space for the nucleophile to attack the electrophile. Right. So there's so much stuff going on right now. I'm going to redraw this like this. right? This is the nucleophile. This is the electrophile. I'm going to star the nucleophile. I'm going to dot the electrophile, right? This star nucleophile is going to attack the electrophile, the dot, and kick out the leaving group. The reason why we have to kick out the leaving group is because this carbon here has two hydrogens that are invisible. We're trying to make a new bond between this star and this dot right here, right? But when we do make that new bond between the star and the dot, that's going to make 5 bonds on this carbon right here, right? 1, 2, 3, 4, 5. That breaks the octet rule. So to conserve the octet rule, we have to kick out a bond. And then we're kicking out the bond with the group that can hold that pair of electrons, which is this bromine here, right? So if we were to predict the product, Br would leave with an extra pair of electrons and a negative charge. And this is considered a good leaving group because that bromine with the negative charge is relatively stable. Since bromine is highly electronegative, it can hold that negative charge well. So now to predict the product here, I'm going to draw in the dot right there, right? These hydrogens are invisible, so I'm not going to draw those hydrogens in again. But it's no longer attached to the Br because the Br went bye-bye. It went like, it got kicked out as a leaving group, right? So now we're going to make a new bond between the dot and the star right here, right? That's the new bond that we just formed. That new bond that came from this arrow right here, right? This pair of electrons. If I highlighted this pair of electrons like that, that's going to be those 2 electrons right there in that bond. That pair of electrons made that new bond between the star and the dot. Now we just have to attach what's attached to the star, which is a triple bond like that and ethyl group like that. So the final product for this SN2 reaction would be this right here, where we just have this alkynyl anion attack the electrophile and kick out the leaving group like that. SN2. Any questions on that, Wiley? Did that make sense? Okay. Now let's move on to the next one with the secondary substrate. Secondary substrate here. What the? Over here. Okay. Okay. Third one. So we're gonna bring in that alkynyl anion again, but this time we have a secondary haloalkane, right? Because we still have a good leaving group, the bromine, but this electrophile here is now secondary because it's attached to 2 other carbons. And for this reaction, if it's secondary, we're gonna do E2 reaction, right? The last one, if it's a primary haloalkane, SN2. If it's a secondary haloalkane, E2. So this is your alpha carbon. These are your beta carbons. Draw out at least 1 beta hydrogen for each beta carbon. And then you're going to go for the Zaitsev E2. Zaitsev. Because this is considered a small base. So we want to make the more stable alkene. Right. It's going to be grabbing the most substituted beta hydrogen, which is this one here. So this base here. So in the previous example, that acts as a nucleophile. In this example, it's going to act as a base, which is going to grab this most substituted beta hydrogen. The bond between the hydrogen and carbon, beta carbon, is going to make a double bond here. And then we're going to kick out that leaving group. All those 3 arrows happen at the same time. Grab the hydrogen, make the double bond, kick out the leaving group to create that alkene. And you could have this terminal alkyne with this hydrogen back, where that hydrogen there is this hydrogen right here that it grabbed. Okay. Yeah. Okay. See. So yeah, I'll and Alpha's hours here, but Camilla, did you have any problems while you were working through these chapter 22 problems? I could go over that here and then I could do the rest tomorrow in the office hours.
Oh, don't worry. I think I got all of them. I mean, I
Uh-huh.
can send you a picture, but
Yeah.
I did. I mean, you
Uh-huh.
don't have to do it now, but I did send you a picture of some questions that I had. Like,
Uh-huh.
where does Like for nitration, bromination, like Friedel-Crafts, like where does it
Right.
add?
Okay, yeah. We can go over that in tomorrow's office hours at the beginning. That the problems that you sent tomorrow.
No worries. Thank you so much.
Yeah, no problem, Camilla. Okay. Yeah. Let's see. I How are you guys feeling about your midterm tomorrow? Elysia. And when do you have your midterm, Marley? Mhm. You have a quiz this Friday. It's all about mechanisms. Oh, like the alkyne mechanisms. Oh, and the alkene, some alkyne, all the alkene mechanisms: hydroversion, oxidation, oxymercuration, demercuration, uh, uh, hydrohalogenation, halogenation mechanisms. Yeah. The osmium tetroxide. Yeah, osmium tetroxide. Yeah. Grind that Levin's practice worksheet, because I feel like her practice, well, for her 118A class, the practice that she provides is harder than the actual exam, but do it in timed conditions. Like, try to time yourself to practice the time conditions, or if not, you could. It's like 50 problems. Yeah, so you could do like, let's see, 1, 2, 3, 3, like, we can get back with 3. You can do like 15 to 17 a day from today. 15 to like today, 16 tomorrow, like, and then like 20 something on Thursday. Like, you split it up somehow, or try do it all, grind it all tonight, and then review it tomorrow, and then send me that practice worksheet, and then I can create similar practice problems for you on the office hours as well. Yeah, send me that practice worksheet. I want to see. Yeah, let's do it. You got it. Yeah, do some today. Do some today, and then try to finish them tomorrow. And then on Thursday, just do similar practice problems, or review the problems that you've been doing. Yeah. Okay. Let's see. Yeah. Okay. Let's see. Are you feeling better for your exam tomorrow, Elysia? Okay. I'm gonna end the office hours here. Good night, guys. See ya.